Hi guys. Now, first of all, thank you very much for joining this webinar. And this webinar, as you already know, it is on the design of industrial RCC foundation, especially pile foundation for industrial tank, acid tank. My name is Abhishek Panda, and I'll be the speaker for this webinar. Before that, I would like to brief you that this webinar is the first webinar of its series, and we will be conducting the several webinars in just coming future, and it will be counting like that. You may browse through our website that we are basically consulting engineer service, but later we are into the training because we feel that there is a gap between our academics and what is expected in industry. To bridge that gap, we have started this organization, AANKHE Training Club, and under this these webinars are being conducted, which is absolutely free for just enhancing the knowledge level, and also we will be happy to know what are the lacks or shortcomings that we are facing, because it will be a knowledge sharing platform. So now, without further delay, let us move to the topic. As you can see that the topic is analysis and design of a pile cap, including piles also. Though the geotechnical aspect of pile is not properly dealt with in this webinar, because this will be dealt with in several other webinars. Especially our concern is to how to design a pile wrapped or a pile cap using Midas Gen application, and just to compare it with the pile reactions that is obtained manually and using the software, right? So for that we have several we have several entities, and that means it is divided to several parts. For your easy understanding, it will be something like a project type thing. Let me brief you one thing, that when you go to a project, from its very beginning, a project planning is very much essential, because planning is something like, it also it saves the cost, and also it saves the engineering man hours, as well as a proper planning is nothing but a green signal to a proper execution. Without proper planning, you cannot properly execute, and especially when it comes to the thing as far as grey field projects are concerned, that means a modification or a new construction inside a periphery of already developed area like industrial area. So their planning is of utmost important. So without planning, you cannot even proceed. So from very beginning, actually project planning is the very beginning stage. It is followed by the engineering. Engineering comes into several aspects, starting from civil to mechanical to electrical to ETC and process. As far as plant is concerned, there are several engineerings are concerned. It depends actually on the project. Even architecture, if it is a building, then architecture and the services, etc., etc. But thing is that under the engineering, first also you have to have a clear picture of your project. Then after that you have to choose suitable methods. For example, for this project I am saying, you have to opt for either you can go for a manual or you can go for software based, right? So if you have available with you a proper software, then you may go for that, and otherwise you may take the manual, and also time analysis is there. From several different aspects you need to see it. Then coming further, after engineering, the execution begins, but during execution there are several challenges are met with, because as per our assumptions, the practical field might not be like that. So as per natural requirements, or as nature desires ultimately, because this from starting from soil profile to completion of the project, there are several hurdles are being faced, which are actually not planned, right? Because we do not know that these hurdles are going to come. So these needs to be tackled with using proper engineering. So it's a something like the two sides of a coin, right? Engineering and execution generally goes side by side, but again another thing also comes, that is PMC, that is project management. And the project management is nothing but a bridge between execution and your engineering. So ultimately everything comes under engineering. So after completion, the project is completed and it should successfully run. But as far as engineering is concerned, the majority of the engineering role is limited to the engineering part, that is the second phase, followed by the third phase, starting of execution and PMC. Right. So here, without further delay, let us come to the analysis and design part, and let us start the slideshow as well as the software application. Please stay with us for that, and we'll be very happy for that too. And this series will be continuing in the coming future for several other aspects, not only just structural engineering and not only just industrial thing. It will be spanning from architecture to mechanical, from drawing, drafting to the process engineering. Everything we have and we can do, will be doing. And the authors will be also from the practicing engineering field to the academics. We'll try our level best to bring academicians, authors, as well as practicing engineers from industry, as well as from the building sector, from architect side also. We'll be trying to do that, because everything has some roles, even from the structural drafting part as well. So we'll be trying for that, but let us start this webinar first. Thank you. Let me start this webinar. Without further delay, we should start, because it is going to be already a long session. So we have divided our today's webinar to the following, that the topics to be covered you can see here, and these are the topics to be covered. And for now, in the very beginning, that is introduction to Gen, what we'll be doing, that we'll be providing a brief introduction to Midas Gen. Actually, we're providing very brief introduction to Midas Gen. Actually, this is the software originally developed in Korea, and I'll be coming to its history actually. So after that, we'll be going to project overview. Project overview means I'll be showing you a drawing where how the project is given and how you need to plan, right? So keeping in mind all these things, actually whatever things we are covering here, this will be a very speedy process, because a webinar is just not enough, because it will be taking a lots of time. In this project has taken around more than a week by a team of engineers. So this project has taken more than a week by a team of engineers, so which you cannot actually expect to be delivered within 1 to 2 hours. So we'll be going very fast, and also there are lots of pros and cons are there that we have faced during this project, which will not be elaborating in detail, because it will take a one week time for elaboration, because we have faced that. So we will be giving you the results, so that it will be giving you brief idea and it will enhance your knowledge. Then I'll be showing you the conventional analysis in brief. Under this conventional analysis, I'll be leaving the pile cap, because pile cap analysis I think is not required, since we'll be doing it using Gen. I'll not be doing it manually in a conventional method. What we'll be doing, I'll show you how to calculate the pile reactions using the rigid plate theory or the conventional method, and assuming pile cap as rigid, we'll be getting the detailed idea on the proper loading and how the pile reactions are distributed. And there we can also go for a comparison with the software. Then I will be jumping to the mathematical modeling using Gen. So in this method I will be just briefing you regarding the requirements of FEM in very brief. If you know FEM only you can understand. If you do not know, then you should get it by heart, because again FEM is a semester course which we will be delivering, but in a very slow process. In a webinar it is not possible, but you can just remember the rule of thumb of FEM for modeling, and since it is a very simple structure, it will not be that much of tedious to understand what I will be saying. Then the mathematical modeling, I will not go through the formulae, because going through formulae of FEM is actually not required for the project. It will be taken care of by software. Midas is already a internationally operated software, and after seeing the details of Midas, you will be understanding how vast this software is actually. So we need not challenge the authenticity of software, and all these theories and the mathematical equations are taken care of by software itself. I will be showing how to model it in step by step. Then we will be jumping to the FEM analysis and results. Under this part I will be analyzing, and I will be going to post processor to show you in very brief about the results that are given by the Gen. Because once if you are acquainted with this software, you can find it your own, and if you demand, then we will be going for another webinar on this particular topic to show you a detailed elaborated analysis and side by side results. Because everything, as I already said, it is a 1 week effort taken given by our team, which you cannot expect us to deliver within 2 hours. So up to a maximum level we have tried, and I will definitely be trying to complete the maximum possible, so that at least you can get the idea and the knowledge level of yours will be enhanced. Our main aim is to knowledge the enhance. The details of analysis, post processor, and the details of equations, these are already written in the book. How to use it, our main aim is to transform the academics to the industry. So how to do it, you need to learn that. You just need not learn the software here. You first try to understand the objective of this webinar, that all these webinars are framed that to enhance the knowledge base, not to impart that software knowledge. So we'll be completing FEM analysis and results using Gen. Then we'll be going to the comparison of conventional and Gen results for pile reactions. It will be varying a little because FEM is a numerical software, and also it takes a realistic modeling. Under conventional analysis we go for several assumptions, so the results will be little bit varying. It's okay, I'll be showing you the comparison between the Gen and conventional results. Then I'll be showing you the design, which is a very vital part of this software. You can conduct a design using your hand calculations as per the conventional analysis. In brief, I'll be discussing, though I'll not be designing the cap, but you can design on your own after getting the pile reactions. So you can also compare it. If you are interested further, we'll be going for another webinar by designing it manually. I'll be designing it manually and I'll be showing you how to do it manually. Then we can go for a comparison between the conventional analysis results and that to our software based result. Then lastly it comes to the concluding remark. Actually there is no concluding remark to any webinar. Once it is completed means it should be understood, and if it is not understood, then there is no meaning of a webinar. Actually it should not be like that. So there is no actually concluding remarks, but the question and answer will be the best concluding remark. If you have understood a little even from that, if you are then you can go for any questions and answers. It will enhance the knowledge, and also you can go for questions after this webinar as well. We'll be trying our level best to provide you answers in the coming future. But however, this webinar will be giving you some 10 to 15 minutes times. Those who are interested to ask questions, I'll try my level best to clear there. If not, then we'll be doing it in future. We'll be in touch, because this series of webinar will be continuing, and as per your demand also we'll be trying to bring the webinars. Right, so without delay, let me move to the first slide on the introduction to Gen. Here the history means every software has a history. Like you must have heard about Bentley and your tabs and several other softwares, Tekla structures, etc., etc. Similarly, Midas Gen was actually developed in South Korea by Midas IT, which actually was a R&D part of POSCO. You all have heard, I think, on POSCO. So it was a R&D wing. In 1980s it was developed actually, but it came to market after 1990, because the internal management decided to go for a software reselling instead of developing for their own use. They thought of going for a software reselling. It is already a finite element software from its very beginning. Unlike Bentley's START was actually matrix method software. Later it was into FEM. However, in the Gen, it was from very beginning it is a FEM based software, and from very beginning also it is a very user friendly software. It is unlike other software. It was not a resource software. It was started to be applied in the field. It is unofficially what you can see, though you will not be finding any official statement, because by the time the name came Midas Gen, before that also this software was used by the internal team. The plant structures, the power plant structures of POSCO and South Korea, and some of the mega structures were built by the internal team as well. But later they thought to go for the commercial version of the software, so they name it as Midas, and just formed the Midas IT. So in the project list we will not be finding any project of any plant structure before 1990, because before 1990 this software existence was limited to their circle only. So after 1990 it came to picture, and from that it has carried out analysis of several mega to super tall structures, from the building to tanks, and in several areas. We'll be showing you some of the mega building projects only, but as far as application of Gen is concerned, it is expanding to a very wide area. You can apply this software from buildings to bridges, from tank structures, from thickened slab to solid elements, and you can also apply for heat of hydration analysis, for normal vibration dynamics, and as well as fluid flow. For fluid flow, CFD software is there by Midas, but Gen you can use that for your wind tunnel data. It can be used in Gen. So several the application of Gen is not limited, or it is very huge. And also I will be trying, and our organization will be trying our level best, that we will be showing you several projects of our own using this Gen, and will be also tallying the result of the software to the conventional, so that you will be also convinced that this software provides the results as desired. So it's not like it is not limited to building, because many people actually have idea that it is a building software. It is not building software, it is general software. Unlike ETABS, you can see, you can comment that it is a building software, but Midas Gen is general software, because every software has their pros and cons. But when you comes to generalization of software, always remember that a general software have wide area of operation. That means, for example, let me tell you, in ETAPS, if you do not provide a diaphragm, you cannot apply the seismic loads, right? But here in Gen, without defining the diaphragm, you can also provide the seismic loads, right? So there are several things are there. Many people, those who are acquainted with other softwares, they may say differently to this opinion. So it's up to them, because whoever is using a software, he or she knows only the pros and cons of it. But as a comment, the general software actually lacks boundaries, because it should be it should have very limited boundaries, because if it is imposed to certain range, like if you only impose to buildings, yeah, then you have to provide boundaries so that the software cannot be used in bridges. But such things do not exist with Gen. Application spans very wide range, though some of the mega projects using this software will be showing. Please have a look into it. All these are buildings especially, but in near future we'll be showing you our software applications to our several other type of projects, which you will be understanding that this software is a general software. So guys, let us start the project overview, because without further delay and wasting time in introducing the software, let us come to the point for which we have arranged this webinar. And our first point comes understanding the client's requirement. It is very basic point which needs to be understood by engineers, because without starting prior to starting a project, you must understand the type and nature of project, and whether it is a completely new greenfield project or a greyfield project, and its approach for its completion. Then comes a possible environmental impact. So using your technique for construction of that project, whether it will be a environmental issue or something like that, you have to keep in mind. In our case, actually it is a acid tank, so you have to be very careful regarding that. So the acid should not get away from the tank or should not leak, otherwise the entire area including your foundation will be destroyed and possibly may lead to collapse. Then your detailed dimensioning of tank and foundation system, since it is as we have already told you that it is inside a plant, that means it is not a greenfield project, though the project is very new, but the space is very constrained. So keeping it in mind, you have to plan accordingly so that the other facilities or other available structures do not get any impact due to your construction. Then your limitations again include your limitations regarding boundary and existing structures. So let us just bring the project how it looks like. Let me explain you. Now this is our project. This is our project where your tank, you can see, let me call the screenwriter. Okay, so here this portion is your tank portion. From here to here, this is your tank, and this one is your 5000 mm, right? As you can see already, since we are bound by some norms and codes, we cannot completely show you the requirements of client, because it will expose ultimately the details of project. But for your information, it is a line where already other mega structures exist, right? here, and they also have lots of piles, right? So we cannot go beyond that, we have to have certain distance. And also here you can also see there is a line, there is a border line that also extends here, which we cannot also touch. And here also you can see these are also the boundary line limitations, beyond which here it is a pathway or road, you may say, and these are the drains. So you cannot break them, right? So ultimately we only have this area which we can use it properly, right? The diameter of tank is 6.55 meter, it is already mentioned here, and your tank to your drain wall distance is 400 mm. This one is also mentioned here. And I think you have got an overview of the project till now, which I just took the project to the CAD so that it will be easier for you to understand. Let me open the CAD file. So now this is our CAD file. In this CAD file I'll be explaining later regarding this. Here you can just see your this portion is your pile cap, this is center line, a pile, outer periphery, right? And this one is your tank OD, that is outer diameter, right? Already the dimensions are mentioned here, 5000, tank your total pile outer to outer 6550 mm, all dimensions are in mm. And I have also mentioned the corresponding dimensions from here also, from the center line, it is the middle, right? So now, since our main objective will be to demonstrate it, the design using our computer software Zen, but before that we have planned to show you how to take the manual calculation to get the reaction on the piles. As you can see that the piles are in a grid, right? These are in a grid actually. So what will be the formula for the pile cap or the group of piles carrying axial load with a bending? So suppose your axial load is P, this one is your x axis, you can see here it is written, and this one is your y axis. That means my axis is this one x and this one y. So your axial load is P, your EMX is equal to bending about x axis, right? Similarly, my is equal to bending about y axis. So as a whole, your formula for combined axial load and biaxial bending or uniaxial bending. So now what you know, the formula is your P by N, that means number of piles, plus mx ry by ix, plus this is plus and minus both, my rx divided by iy. This is the formula for load. When you take all positive sign, this one is positive, this one is positive, you get the maximum load on the pile. Similarly, when you take all negative, this one and this one, you get the minimum load, or maybe it might be tension also on a pile. Accordingly, you find out as per geotechnical data whether the pile will be able to take the load, then you provide the calculations, right? So for now, actually let me remove these things from the screen. Let me open the writer. Okay, so here we have a blank space. Here we can find or we can write the data. The data is like client has provided your total load acting on the tank is 150 metric ton. That means P tank is equal to 150 metric ton. So suppose you take pile cap as 850 mm. Suppose it is just an assumption. We have not done it yet. So let us assume that pile cap will be of 850 mm. So what will be the weight of tank? It will be your pi by 4 into 6.55 square, pi by 4 d square, into thickness is your 0.85. Now you get the volume, and here you multiply unit weight of RCC 25 kilonewton per cubic meter, or if you want tonnage you can provide 2.5 metric ton per cubic meter. So what will be the value? So it comes around 71.6 metric ton, right? So here the total weight, this one is the tank weight, sorry, this one is your pile cap. So your total axial load will be how much? Your 150 plus 71.6. We can better you assume it as 75 metric ton. Very near about 75. It will be easier also. It is total is your 225 metric ton, right? Okay, so this one is your axial load, but as you can see you have also bending, the bending due to your earthquake, because earthquake force is a sway force, so there will always be a bending associated with it. If we go here, let me go to the CAD file. you find this is your pile cap and piles are projecting like this from the cap. Oh, forgive me for my sweet handwriting. Like this. So this one is your cap actually, right? Ultimately what happens, your tank is installed here. If we go to complete 2D, in 2D you will find your tank is installed here, then the tank is resting on cap, then cap is supported by piles. Here you provide some cover, right? Right. So my objective is your 150 metric ton is acting at the CG here. It is a simple project, so we assume that entire weight is concentrated at the CG. So when you go to the calculation of your seismic force, your seismic force is calculated using Z by 2 into I by R into SI by G, taking zone 3 Z by 2 into I 1.5 divided by 3 into 2.5 as SI by G, we get 0.10, right? That means 10% of the mass. So the seismic force will be obviously acting at the CG as 0.10 times 150. This is 15 metric ton. That means here 150 kilonewton or 15 metric ton. Similarly, the seismic force acting at the top of pile head or pile cap, it will be 0.10 times 75 metric ton, that will be 7.5 metric ton or 75 kilonewton. I hope it is clear to all, and that 150 metric ton acts both in x axis and y axis, but not at a time. It acts at different time. That means either earthquake hits from x or from y, or similarly vice versa, minus y or minus x, the result will be very similar. So my point is to calculate the bending. So in order to calculate the bending, what will be the bending moment? As you already know, the tank, it is a 3.7 meter height. Similarly, the pile cap we have assumed 0.85 meter, right? So here what happens, our total bending moment about your pile base will be how much? It will be 150 into let me remove this portion so that it will be easier for you to understand. It will be 150 kilonewton into how much? Your 3.7 by 2, 3.7 by 2 plus 0.85, will be the bending moment due to the tank itself, plus will be adding 75 kilonewton into 0.85. So how much the value comes? For 68.75, always write down the unit, it is kilonewton meter, right? The value comes to 468.75 kilonewton meter, and it is equal to either mx or my, because it is a simple structure. It is a very it is a circular structure, so it is symmetric about both axes. So let us again return to our board where we left with P only. Now we can add mx as 468.75, which is nothing but how much? 469, or you may take it as 470 for calculation, matlab betterment of calculation in hand. When computer does, it is not an issue. For hand calculation, we always try to simplify and add 468.75 and 470 as very least impact. Anyway, so let me first remove it. So here we go, our bending for 70 kilonewton, and here it is approximately how much? 2250 kilonewton. Now what our formula says, as per our formula, it is P by A plus A or N plus mx ry divided by ix plus my rx by iy. But here in our case, either mx or my, either or we have to choose, right? So in our case what happens, let me again return to the CAD file to show you the calculations. Your total P is ready with you, that means it is the P, right? Similarly, mx my ready with you, you only need your ry and rx and ix or iy. So here we have, since our ix and iy are same and rx ry will also be same, so let us first find out any one side and it will be applicable to the other side. Here bending is uniaxial, there is no biaxial bending. So first of all, let me take this axis as our parent axis, right? So here I have mentioned this one is your x axis, obviously this one will be our y axis. So our ry will be here, this one how much? ry1, this one is how much? ry2, this one is how much? ry3, right? Similarly, your ix, when you take mx, means bending about x, this one is your mx, means the structure rotates about x. So obviously, if we take a rectangle like this, so suppose let us take a rectangle like this. For your understanding, I am just saying this one is your x axis and it is B and it is D, right? So D is total, actually from here to here it is D. Now what will happen if your bending is about this is your mx, this means bending about x axis. So the inertial force, that is the resisting force against bending, will be how much? The inertia will be your ix. So your stress will be how much? Mx by your ix into r, where ix is nothing but bdq by 12 and r is your d by 2. Ultimately it comes around mx by zx, where zx is your bd square by 6. Now my point is, in this case, in case of pile cap, instead of taking all these B and D things, we have to take the discrete moment of inertia of piles, individual piles, right? So you already know moment of inertia I is equal to how much? Your bdq by 12 plus a k square, where a is the area and k is the distance from the center. In our case, our bdq by 12 will be replaced with how much? Pi by 64 d to the power 4, because it is the moment of inertia of a circle, that is, it is the moment of inertia of a pile simply. Then our things comes ak square, where a will be how much? Pi by 4 d square, and k square is the distance from center line to that particular pile. That means here either ry1 or ry2 or ry3. But as you already know that it is d, means it's a very small amount, 0.5 square will give you 0.25. Similarly, to the power 4 will be giving you very less. So ultimately your this value and this value is very negligible. It has very less, impact on the calculation of inertial force. So generally we neglect this and we only take the k square while calculating the inertia that resists the bending. So in our case, what happens? Your number of piles, first let us take your number of piles, n is equal to how much? It is 21. Total number is your 21. Then you come ry1. How much it is? ry1 is equal to 1400 or 1.4, you may take. ry2 is 2.54. These are all in meters actually, and ry3 is equal to your 2.9 meter. So our main aim is to calculate our I, right? So I is equal to here how much? As I have already told you, only will be taking the k square part with us. So while taking the k square part, we will be taking our r1 square, ry1 square plus ry2 square plus ry3 square you can see that the numbers are varying here. Suppose this one is your RY1, this portion, that means from here to here it is RY1, right? So how many RY1s are there? It is 1, 2, 3, 4, 5. So 5 RY1 is there. So it will be adding to the moment of inertia. Now RY2 is how much? This is and this one. So that means 2 RY2 square, and RY3 is only 1. Again, this we only calculated the half circle. In the next half here we get the very same thing. So into 2 will give you the results. That means what? You will be finding 5 into 1.4 square plus 2 into 2.2 into 2.54 square plus 1 into 2.9 square into 2. The value will be 62.2264, which we may also approximate as let me remove from here. Which we may also take it as 62.23, right? 62.23. Now what happens? Your I, this one is equal to how much? Your Ix is equal to also your Iy, both are same. So it is 62.23. Let us go to the board. Now you get Ix is equal to Iy is equal to 62.23 square meter. So what is your Ry or Ry1 is equal to your Rx1 is equal to 1.4 meter. Similarly, your Ry2 is equal to Rx2 is equal to 2.54 meter, and Ry3 is equal to Rx3 is equal to 2.9 meter, right? So now what happens? Now let me again go there. here you see all the loads will be shared. As you know, it is P by N. First of all, the axial load will be shared equally. What about the bending load? Bending is how much? M x by Ix into Ry. Again, let me split it. It is Mx is your fixed amount. What about Ix? Ix is nothing but a summation of your twice into the summation item. That means it is also a fixed amount. What is only your variable is only this much. This only varies. That means this one is your constant and this term is your constant. Only varies is this. That means whichever point is the farthest point, that pile will be stressed severely, isn't it? Whichever point is lying away, that point will be stressed severely, because ultimately this one is your numerator part, this one is your denominator part. The numerator part is more, means the force will be more. Here you can simply also apply the unit. This one is your kilonewton, you divide by a number, that means you get only kilonewton. Here it is kilonewton meter, here you get meter, and here it is square meter. Meter, square meter get cancelled. You also get the kilonewton, that is the force. Ultimately both of them are added up. So obviously the highest pile will be stressed more. This is as per the conventional analysis or rigid plate theory method, where we assume that the entire pile cap is a rigid element and it distributes the loads uniformly, right? Now let us come to the portion. Now let us come to the board, and we will be using that the highest point R3, right? This one is your Ry3, which is nothing but this one you are taking from here to here. Similarly, if you take the axis from here to here, will also be same. This will be your Rx3, Ry3, x3, both are same. Now the farthest point or maximum possible load will be how much? Your pile cap, it is 2250 by 21 plus our mx is how much? 470 into that you will be getting Ix is your 62.23, sorry, this will be divided 62.23 into your Ry, which is nothing but 2.9 meter. You get the load. What is the value? It is coming around 129.04. This is the maximum load expected on a single pile. Maximum. This is your P max. The maximum load expected. Similarly, what will be the minimum? Simply provide a minus sign here. By providing a minus sign, we get, this is due to the plus sign, this is due to the minus sign, we get 85.24 kilonewton. This is your P minimum, which is greater than 0. That means no tension. This ultimately implies there is no tension in the pile. Again, I would like to add, many geotechnical engineers will not be in line with my assumption, but generally I considered it during my designs that when we are taking a pile, now in all these loads, this is the tank load and this is the cap load. So where does the pile load, that is the self weight of pile, it is a pile, right? So where does its self weight goes? It is obviously taken care of by pile itself. Many people assume that no, it is included in the factor of safety or something like that, so we will not be taking the pile load. But again, after all these permutations combinations completed, I would like to add that we should take the self weight of pile. So what is the self weight of pile? Now let us calculate the self weight of pile. It is a very small calculation. Now here self weight of pile is equal to how much? It is pi by 4 into our pile dia is 0.5 square, pi by 4 d square into h is our 10 meter into our pile length is actually 10 meter, here to here it is 10 meter, and the dia is 0.5, okay, into 2.5 or 25 kilonewton per cubic meter or 2.5 metric ton per cubic meter is the RCC unit weight. The value comes 49.08 kilonewton. Let us take it as 49 kilonewton, right? So ultimately we need to add. Now P max again increases. How much? It is plus 49. So ultimately it comes how much? 178. Let us ignore this 0.04 because we have already taken higher load in case of our pile cap also, right? So we need not take it. So now it is coming 178 kilonewton. This is our unfactored load. Remember, all these things are your service load, that is unfactored. Now for factorization of what you take either 1.5 dead load plus 1.5 live load or 1.5 dead load plus 1.5 earthquake load, right? So since another factor is also there, 1.2 your dead load plus live load plus earthquake load, but this combination is not possible here because in case of tank only live load comes when there is the question of maintenance, and as you already know, the maintenance load is not taken inside the seismic weight, right, or it is not calculated in seismic lump mass calculation. Also during maintenance the tank remains empty, so there is no meaning of taking these combinations. It is engineering, actually as an engineer you have to decide what are the practical cases. So ultimately what you get, the maximum load on the pile will be how much? The maximum load on the pile will be your 178 kilonewton. 178 kilonewton. It is the maximum load on the pile. Let me give it a separate color. This one is your 178 kilonewton. 178, right? So you have to design such that the soil can take this 178, and structurally the pile should be designed as 178 into 1.5 because in structure the load safety factor is there. So structurally it should take 178 into 1.5, but as per the soil theory it should take your 178 kilonewton only. So here it comes to 67. Structurally it should be able to carry to 67 kilonewton load, whereas from geotechnical consideration it should be able to take 170 kilonewton load. Now the point is, you should now see whether the assumption of 10 meter 0.5 dia pile is safe or not. For that you need to go to your geotechnical report. So here we go. Due to the constraint in disclosing the information, we have kept it the left side as blur. Obviously it should be, but my point is not like that. My point is, we have calculated for 500 dia piles, but instead at site the pile available was 450 dia. Maximum 450 dia pile was available at site. So you can find, let me bring the writer. Here you can find the pile dia 450. This one is also 450, but our concern is this particular 9 meter. Here the cut-off length prescribed is 1.36, that is, you may also reduce it. I have reduced it to 1 meter, right? So ultimately my pile length comes 10 meter. Here what you find, for 10 meter your vertical compression is your 19 metric ton and uplift it is your 8 metric ton only, and lateral load capacity in fixed head 5 mm and 12 mm. In our next or in the upcoming webinars I will be explaining the fixed head type and what it means. You just imagine that the pile in a group and tied with a cap is assumed as a fixed head pile, otherwise a freestanding pile is assumed as a free head pile. In this case the allowable fixed head deflection is 5 mm. So total a single pile can take 7.88 metric ton of load at 5 mm deflection at fixed head. So now you have to remember that first of all your total maximum compression can be taken as 19 metric ton or 190 kilonewton. Uplift is your 80 kilonewton and lateral is your 78.8 kilonewton. Right. So let me come to our calculation part. Here our maximum load comes in this case 178, whereas earlier you have seen that our capacity is 190 kilonewton. 190 kilonewton is our capacity. That means we are at safer side. Similarly, actually there is no tension here. I have already checked here. There is no tension. That means there is no need to consider the uplift. And further it comes the capacity of pile in lateral load resisting system. Our lateral load is how much? The earthquake load. The earthquake load is how much? It is, as you have already seen, it was how much? 15 metric ton earlier for the tank, and for cap it was 7.5 metric ton. So which sums up to how much? 22.5 or 225 kilonewton. Right? However, our one single pile is capable of taking how much? 78.8 kilonewton or 78.8 kilonewton can be taken by a single pile as a lateral load capacity. So for 225, how much pile do you need? 225 divided by 78.8, it comes around 2.85 or let us take 3 piles. But in a group we already have 21 numbers of piles. In a group we already have, oh, I have removed, no, here we have 21 numbers of piles. Since we have 21 numbers of piles, so this is perfectly safe. Another point I forgot to mention, when the piles, let me remove this portion. As per theory, what happens, suppose the distance, the center to center distance between a pile without under rim is above 3d. Suppose this one is our d, diameter of pile, this is above 3d, greater than or equal to 3d, then there will be no reduction. That means no reduction of group, no reduction of pile group capacity. But if we take pile to pile as 2.5d, because less than 2.5d is not allowed at all. 2.5d, where this one is our d. Then the group capacity reduces by 10%. So in our case, what we have taken, since we have taken 450 dia piles, so 2.5 into 450 is equal to 1125 mm. We have taken the list. Let us go to the CAD. Now we have taken the list capacity as 1140. This one. That means here also. That means if we take 450 into 3, it comes around if the spacing between the piles is less than this, if S is less than this, then 90% of total group capacity will be considered, right? So in our case, what happens, you have to consider the 90% of pile load capacity. So our pile load capacity is how much? It is 190 metric ton per pile. So but our loading is how much? Loading is our 178, right? So 190 into 90%, this comes around 171 kilonewton, which is less than again 178. But the fact is, code allows, IS 2911 code allows that the pile group as a whole will be reduced by 10%, whereas the single pile can be overstressed to 10% as well. That means, try to understand, the closed spacing of the piles, that means if it is less than 2 point if it is less than 3D, so the pile group capacity will be reduced. But if it is required, like in our case, just see very close contact, it is 178 and it is 171, only 7 kilonewton difference. In this case, code allows you can take the overstress in the pile, that is per pile you can increase 10%, such that the group capacity increase 10%, but per pile you can increase 40%. Sorry, actually per pile you can increase maximum to 40%, whereas entire group capacity increases 10% only. That means during bending, you can see here some piles are getting less load and some piles are getting more load. So these individual piles may be stressed to 40% high, but overall the group capacity, that means if I have taken the capacity of one pile is 171, so the group capacity will be 21 into 171. So this 21 into 171 can only be increased to 10% as a whole. And now if I increase, suppose forget about 40%, if I increase 10% overstressing, that means my 171 kilonewton capacity of pile will be able to taking how much load? 171 into 1.1. It will again come as 188. That means this will be 188.1. So let us neglect 1. This will be your 188 kilonewton. So this is higher than the 178 kilonewton. So our motto is achieved. So this is the most economiest design as far as conventional method is concerned. In this case, we have totally not wasted the material, right? So engineering should always be focused on safety first, but that doesn't mean that you make the structure uneconomic. You have to do economic design by considering utmost safety. So in our case, safety is achieved and economy is also achieved. Now my point is, instead of going for again conventional calculations, I would like to do it in software, because our motto of this webinar is to present it in the software, right? So let us move to Gen. So coming to the next slide. Now since we have completed how to do it on manual calculations, without further delay, let us move to the computer part for the modeling of the tank, followed by the design using Gen. So here what will be learning in this session? First, importing geometrical model. That means we'll be importing the what you calculated manually, we'll be importing it to the computer from the CAD file through MS Excel, and then we'll be modeling and provide the material properties. If you are acquainted with APM, that is finite element modeling, then you must be knowing that without material properties and boundary conditions and without proper nodal connectivity, it doesn't work. I'll be showing it step by step. Then we'll be providing the boundary conditions and load applications. So in this slide we'll be covering these three. So now let us move to the modeling part without further delay, and one by one we'll be covering. So these are my files. And these are the distances mentioned from center to last possible pile, and since it is circular and symmetrical, so it will be applicable to both x and y axis. I have provided only through y axis. If you can see, you can find y axis is written here. Then for the towards what we have done, in order to import the model to our Gen, first we have to import it to our Excel program. So because it will be easier for working with that. So I have done, I have taken lines connecting the nodes. Here are some of the nodes. Similarly, you can find a tank of total 5 meter dia is here, and you can find the value written here. It is 5000, means all the dimensions written are in mm. That is 5 meter dia. Entire your pile cap is, you can find here 6550, that is 6550. Okay, so let us remove all these things and come to the we found the points here: x coordinate, y coordinate and z coordinate. How to import to Excel? It is actually CAD operation problem or CAD operation features, which I suppose you are well acquainted with that, because so our webinar is based on mathematical modeling, not on the CAD operations. So I assume that you know the CAD. Here, this one is our x-axis and this one is your y-axis. Simply, this is y, this is x. So the axis perpendicular to the board is the z-axis, which you cannot see, but it is in the 3D. If you take the 3D, you will be able to see, and we will be seeing it in Gen. So I have taken the coordinates, the nodal coordinates piles of the tank. Here we have taken the coordinates because presenting circle in form of a linear element is more easier for software. Similarly, the outer edge of pile cap we have considered, and like this we have taken the things to our Excel. Let us close it. So now we will be copying all the coordinates and putting it in our Gen. Before that, we need to open the Gen. So let us open the Gen. Now you guys already have had an intro about Gen, and it is Burj Dubai, earlier known as Burj Khalifa. This was the main software. So now it opened. First of all, let us save it. Now our screen is fully ready, and now without that, without proceeding to that, we need to define the properties so that it will be more easier for us to identify. First, let us go to the properties and find the material properties. First we need to add, it's a concrete material. Material ID is 1, and in the name you can simply type concrete or CONC as you wish. Then type of design is your concrete, and here it is Indian standard ISRC, and since it is in adverse environment, so we have taken M30 grade concrete as minimum. So since it is already fed into the software, all these things are like modulus of elasticity, it is Poisson's ratio, thermal coefficient in Fahrenheit actually, and weight density. All these things are already predefined by the software. This is based on the code and etc. If you do not want to do these things, you can select here as instead of selecting the code, you can select user defined data. If you go to none here, you can manually put the data here. You see it is blinking, but we'll be using the code. This is IS and grade of concrete is M30. Right now click OK. Your concrete material is saved. Next, move to the section properties. In the section properties, we'll be dealing with basically the piles. So here you can go to add. So now we need to come to the piles. So here first let us select a circular section, solid round, and go for the name, that is pile. .500 dia. Okay, so here select user and provide it here as 0.5 meters pile diameter. Oh sorry, it was actually 450. Yes, it was earlier it was 0.5 anyway. So now let us come to again add. We need to define the tank. As you know, the tank diameter is 5 meter. So here we need to go for a pipe section. Instead of modeling entire plate as a tank wall, because that our main focus is to design the foundation only. We are not concerned about the tank walls, so we are taking it as a 1D element, and you can select the pipe simply, and you can provide the name as tank. And go to user. Total diameter is 5 meter and the thickness is 10 mm, means 0.010 meter. Click OK. Now our two section properties are defined. Now let us go to thickness. The thickness will be used for the modeling of pile cap. Actually, for thick pile caps, solid element modeling is adopted, but since this structure is a very simple structure, it is not that much of important, so we are using the thickness of plate element. Instead of going for solid element modeling, we are going for plate element modeling. And also with plate element, Midas has a stabilization scheme for thick structures. The vertical stiffness of the plate should be considered using drilling degrees of freedom. That part will be explained later how to use it. For now, let us go to R, and thickness ID is 1. Let us give the name as pile cap and thickness as 1 meter. Actually we have taken 0.85 meter, but for now let us keep it 1 meter, and later we'll change it to 0.85 meter. Also you might change it here now by going to modify, and you can change it as 0.85. No issues, and simply click OK. Now our properties are defined, but before that, since we have only defined the material as concrete, we have to go for the steel material definition, because tank is a steel structure. So here you can add material ID and name as mild steel, MS, and type of design is steel. It is code is Indian, and you can select E250. That means it is a mild steel, that is the yield strength is 250 MPa, and all of the values are auto populated here. Simply click OK. So while adding or defining the sections in the geometry, these things will be coming into picture. Now go to the Excel program. Here you have to copy the nodes X, Y, Z. Simply copy, then go to the Gen, and here go to node and element, and go to the node table to paste it. Here you can directly paste. So after pasting it, you can go to the UCS, and you can see the nodes are here, and simply you can go to the top view to see it. You can see it is in the shape of your CAD file. Like here you can see the CAD file, it is in that shape. So now let me identify the piles. I'm just clicking on the piles, and these are my files. These are the piles. So the piles are of 10 meter long. So now let us go to isometric. This is our isometric, and here simply go to extrude command. Yes, to go to extrude command, then it is line element. You can here you have to select the material. It is concrete, and it is pile of 500 dia. Beta angle, let us keep it 0 degree. There is no need of any rotation. If you have completed your STAAD Pro, then you must be knowing what is beta angle is. Otherwise any software, it might be STAAD, it might be Zen, it might be tabs, whatever software you have completed, it is up to you. So now it will be, again it will be translate type project, that will be translating, and the element type will be beam element instead of truss tension. You see, pile is ultimately beam element, means do not think that pile is a beam. Beam element means a 1D element that is capable of taking 3 translational and 3 rotational forces. Similarly, a truss only can take the axial load, and tension compression means they are only capable of taking either tension load or compression load. But unlike them, pile can take 3 translation as well as rotation. That is why it is a beam element. So we have to provide equal distance. Simply it is in the Z direction. You can see it is X global. This is G for global. This is global X, and this is global Y. So ultimately another axis lies here. This is global Z, right? So for global Z, since we are going down, because pile will be obviously going down, so we'll be providing a minus there, dz. So let me put it here, just remove, just mark here. This will be minus 10 meters. Actually, for pile, later in several webinars will be showing you, when we'll be coming with a particular specific pile webinar, we'll be showing you how piles are modeled as a soil structure interaction. But here we do not have that requirement actually, because pile consultant has already given the safe load carrying capacity. We only need to structurally design it, and also this webinar should be simple and understandable to all of you, because it is the first webinar. Later we will be expressing and will be digging more into how to model a more economic structure using FEM. That part will be dealt with later. So now let us remove it from screen. So now you can apply here. So you can find that simply the piles are now available to you. Now what to do? Now go to again the top, your front view, that is view from -y, and select all the nodes, because piles are now with you. Now go to the view, activate view. So what happens now? It is, I am in the top view. Now again my tank is actually my tank area is this one is my tank area. Right? So but what we have done, we have assumed, because due to it is a less important type structure, we have assumed that the tank will be a 1D element with all the mass concentrated at the CG. Obviously it will be the CG. So what we have to do, that we need to translate this particular node to the tank height, right? So we need to translate it now. Let us remove it from screen. So now let us come to our tank. We have to model. Now select this node, right? I have selected this node. Go to your isometric. Now we have to again extrude it to the tank height. First of all, it will be a beam element. It will be a line element, node to line, we understood it. Then it is a beam element. Simply there is no truss, tension, compression. Tank is nothing but a hollow beam, you may assume that. Then comes to, it is a mild steel, so it is MS. Then it is a steel tank. The property of steel tank will be taken care of now. There will be no beta angle. Now it will be translate equal distance. Only you have to change the Z. -10 is showing it as we already earlier have taken the pile, but the tank height will be our 3.7 meter. This is as per the client data. Then apply. So you can find the tank. Now let us go to the negative zoom and you can see the tank, right? Your tank is taken care of. It is very simple actually. Modeling Midas in Midas Gen is very simple. Now your tank periphery is this, which is already covered, right? I hope you all have understood till now. So now let us again go to modeling up our pile. Go to our front view. Now select the nodes leaving the tank and activate. What happens before proceeding to that, I would like to tell you one thing, that the beams needs to be there to define a geometry, because what happens, for proper meshing there should be a line element. If we do not provide a line element, then while meshing, Midas Gen might provide the mesh like this or something like this. So while applying the load, will be facing issue, because the tank loading, the tank, whatever you see here, the tank load is up to this. All the fluid, weight, etc. will be acting within this periphery. So if Gen takes a plate element like this, then unnecessarily this portion will be loaded. Either or you have to leave this. Either it will be underloaded or it will be overloaded. If you take entire plate, it is overloaded. If you leave this plate, then it is something like this is a void. So in order to avoid that, we have to guide the software to properly mesh the our pile cap. Why meshing is necessary, I do not tell it, because you all know why meshing is necessary. Let us remove it from screen. Now let us create the elements. And in the automesh planar area, method is the line, and to use this line, I have drawn these lines. So it is a line elements it will be reading. And type of plate is quadrilateral. As you might have known, there are several type of plate elements available. Either they are belonging to Lagrange family or Serendipity family. Here we will be taking the quadrilateral, that is 4-noded Lagrangian plate, or simply you may tell it as a quadrilateral plate. And next we come to mesh the inner domain. Yes, we need to mesh the inner domain. Inner domain means inside the tank area, and include interior nodes, obviously, because without taking the nodes into account or into connectivity, proper load transfer cannot be done, because it is the rule of thumb of FEM that without connecting the node, that node cannot be transferred with any load. Then include interior lines, yeah, obviously. So what does that mean? That means it is asking to mesh the interior line. Suppose a plate element, suppose Midas Gen creates like this. Here it is a node, here it is a node is here, something like that. So you need to mesh this portion as well. Suppose here Gen creates here, suppose a element is created here, and then Gen needs to create another node here, and it should be, we cannot just say that a single plate to create such huge plate, because also plate meshing has a very big impact on FEM. It is called P refinement. The more refiner you give, the results becomes more and more accurate, because since it is a numerical method, if you already know FEM, it is a numerical method. So the better refinement you do it, it will be approaching to a more converged and more close form solution. However, after certain meshing, I mean after providing certain refinement, that convergence stops, or the tolerance limit becomes stagnant. So after that we generally leave, because after that meshing the plate further will result nothing. Let us remove it from screen. Yes, now come to mesh size. So from hit and trial, actually this is our completed project. So hit and trial, from hit and trial we found the optimum mesh size will be 0.3 by 0.3. Below taking 0.3 by 0.3, it is unnecessarily burdening the post processor and our computer memory. Otherwise the converse result we achieve up to considerable extent at 0.3 meter shape plates. Then element type is plate element. It is capable of bending, like here it is plane stress, means it only can take its load in its plane. In outer plane it cannot take. So but pile cap is a rigid plate, it can take outer plane loads. Plane strain, something like a very long retaining wall is termed as plane strain. It will be more elaborate in FEM chapters. And axisymmetric means a cone type, sail type, or a chimney can be termed as axisymmetric. Here nothing works except plate. So type is flat, material is obviously concrete, and thickness is pile cap PC. So we have taken 1 meter and name is here. Then you have to apply. Now the meshing is complete, and you have to go to here, then go to front view. What I have told you, that I need to delete the beam elements. Now you have to select the beam elements and view. Our job for beam elements are over. Now we do not need these beam elements, simply we need to delete it. So now we have removed all the beams and it is only the plate nodes. Now activate the whole structure. This is our whole structure, and we can simply now go to our 3D rendering. This is our 3D rendered structure. If we go to the top view, this is our top view and this is our front view. Now what is the issue? There are basically three issues arising here. One is the shape, which is not a good looking. Next is the color, because it is all these things are a single color, which we can obviously change. And next what comes, our pile level is up to here, whereas cap is here. Is it practical? It is not practical, because what happens, generally the pile cap sits on the pile. It should be something like that, it should be flushed. So all these options are available in Gen. Will be going one by one. Let me first remove it from screen. First of all, it is isometric. First of all, let us off the node layer. Then we have to go to the our draw, then random color, apply. Here I think it is a very good color. In the very first combination it came. So let us keep this color for our use. And now click OK. So color issue is solved. You can simply find that your pile cap is yellow, piles are in light green, and your orange color is your tank. Now what happens, we need to flush the piles on the pile cap top. For that I have to go to structure, then go to structure type, align the top of beam section with floor XY plane and align top of slab or plate with XY plane. Also at the very same time is a 3D type structure. You can simply also convert the weight to masses. It will be required for your this one for your seismic analysis, but since it is a very simple structure, we will be taking the seismic load as a point load for further conventional or for further making it easier. So you need not do it now. Simply click on OK. Now you see the files are, you can see the file heads are now here. File cap is directly sitting on the file. So this seems a more realistic structure. Now let us further come to here. If you do not understand here, you can simply, now you see the pile heads. Now if you do not understand, let me do it again for you. Without alignment, you check there is no pile head here, right? That means piles are, you can see the nodes. I am activating the nodes. That means the pile head is at the blue color line, that is at the mid of the cap. However, in the same time again align and OK, you can see that the pile nodes are moved here up to top, right? So pile heads are now clearly visible here. So pile heads are now visible here. That means it represents a more realistic modeling, right? Let me update, leave it. Okay, so our modeling part up to considerable extent is completed. Now let us move to the actually the properties has already been assigned. So now let us move to boundary condition. Boundary means there are several types of boundary condition actually present. Out of boundary condition, generally people think that it is your support condition. Let us go to the front view like this. First let us provide the support. You all know, prior to moving to that, let me explain it on screen. Your support will be here, either it is a fixed support or pinned support. Since pile sits very deep into the soil deposit, it will be a fixed support. All the pile heads will be fixed support. But actually what happens when we'll be coming with further webinars on pile, what happens actually, the top some portion as per Baum's chart you may find, let us say it is L. Up to L portion there is no lateral resistance of soil. Actually soil is here. Okay, so for some portions the soil cannot provide the lateral resistance, but after that when a pile tries to deflate, then the soil also provides pressure. It is called passive pressure. That means it is restraining the pile against sway. That means instead, suppose you take it as a column, this column is not completely free, it is restrained by the soil, right, up to this portion, and this portion let us say H. That L and H can be found out from the Baum's chart or several other things when we will be providing webinar on especially geotechnic aspect of pile or geotechnical aspect of pile design. Will be explaining it in more details. For now on, for simplicity, we have considered fixed support at the bottom level and the columns as laterally braced. That means they are laterally supported by the soil layer. soil beneath it. Now you simply D all means there will be no translation or displacement, and R all means there will be no rotation. That means it will be a fixed support. Now let me select the bottom nodes and click on apply. The fixed support is applied here. Okay, so our support part is completed. Now let us go to the load part. Here you already know that there will be dead load of tank and pile cap and piles. Your live load, the live load will be due to the maintenance load. Let us say it is 2 kN per square meter, and because it is industrial maintenance. Otherwise, if it had a building with access or building with rooftop access, means 1.5 kN per square meter, and building without rooftop access will be 75 kg per square meter. It is as per IS 875 part 2. But for industrial, let us take it is 2 kN per square meter. So dead load is over, your live load tension is over. Then what else? Then here comes the fluid load of tank. It will be again coming in the dead load. Then here comes earthquake load. It is a very small tank of height 3.7 meter, so wind will be not that much load that will be considerable to be acting in the tank. So we will be analyzing the structure for seismic, dead load and live load. Okay, and now let us create the static load cases. Okay, the first name will be your dead load. Let us keep it simply DL. Now you can select the type as dead, and description if you want to add, then you may add it is self weight plus tank fluid. It is up to you. Add. Then comes your live load. Simply you may select it is live load, and you may add here as maintenance load, because people ask otherwise what is live load. Then you may add your earthquake load. This is EQ in the direction of X. You may select it as earthquake, and you may select it as X direction. Add. Further to select it is earthquake Y. Actually earthquake Y is not necessary, because it is a circular section. Whatever X earthquake force will be coming, that much force will be again coming to earthquake Y as well. So unnecessarily putting two load cases will be giving same result. I am putting here, but the results will be very much similar. It is Y direction. R. Then we'll be closing it, right? Now let us save it. Now you have to go to the self weight. Very first thing is your self weight. It will be coming under your dead load category. Then it will be default, and it is acting at Z minus, because it is acting downwards. So -1 you have to put and click on add, so that it will be added in the load case. So it is, as you find that it is self weight is added. Then what more? After self weight, here in the tank area we need to apply the what? We need to apply the fluid pressure. So what is the fluid pressure? The fluid pressure is your 150 metric ton as per the client data. Let me open the design data. Yes, it is 150 metric ton or 1500 what? 1500 kilonewton. Your 1 ton is approximately 10 kilonewton. Now if we calculate that 150 metric ton weight is acting on area of how much? 5 meter dia. So what will be the pressure? Simply is pi by 4 d square, 0.25 into pi, 3.142 into 5 into 5, pi by 4 d square, it is 19.6375. Now it is 19.6375 and our total load is how much? 1500 kilonewton. 1500 kilonewton divided by 19.6375 comes around 76.38. Let us take it as 76.4 as total pressure load. Let me write it here. The total pressure load (76.4 kilonewton per square meter). Now let us return to the model. So the total pressure load will be acting in this region. That means we have to select the plates in that particular area. So let me select. So now we have selected the plates using the cursor. Then now we have to go to the view. Now we have isolated the view. So now again selecting here. Sorry, it will be the thickness. Yes. Now if we go to view, now there is nothing selected, only you find the plate, right? This portion plate will be loaded. So before that, I would like to tell one thing which I should have told you in the very beginning, that in the meshing it is a thick pile cap. So here you have to go to the domain, then element, then under element property you have to define it as a thick, because when it is thick element, Midas Gen automatically provides a stabilization scheme. So what is the stabilization scheme? That is with drilling degree of freedom. Every software has its own stabilization scheme. In the absence of solid modeling, since it is not that important, we have chosen to go for simply plate element, but it is a very thick structure. So solid element would have represented a better result. without that, to at least reach to the result of solid element, Midas has its inbuilt stabilization scheme for plate, that is for thick plate, that is with degrees, with drilling degree of freedom. That means vertical stiffness is taken care of effectively by the software. If you consider it as thin, then in the thin element it is only stable, I mean in its plane only. In outer plane it is stable, but the stiffness actually do not account for the induced vibration. Therefore only the thick plate provides the vertical stiffness into account for the structure. So with drilling degree of freedom is chosen by the software. You have to choose. If it is not chosen, you have to tick it. You may also uncheck it as per the requirement, but here it is required. Now okay, you close. So now let us again come to our loading part. We have only completed up to here. Now we have the dead load. So to apply the dead load, we have to go to the plate loads, that is pressure. Now it is defined pressure load. Now you have to select, actually you have to write the name. Let me provide it as a name, that it is your pile cap PC pressure load, right? PC pressure. Now what happens, this is element type is plate, and it will be on the face, directly it will be applied on the face. It is plate type. Then the load case. For dead load we have taken as how much? Your pressure is here, we have calculated and saved the data as 76.4, that is the total pressure load per square meter. So we have to provide P1 as minus 76.4 kilonewton per square meter. Similarly, on the tank area there will be always a live load, right? That live load will be what I have told you, that it will be minus 2 kilonewton per square meter, that is for maintenance. You can put directly here also minus 2 kilonewton per square meter. While assigning, it will be assigned to both the load cases simultaneously. Let us check. This is art. Then you may close it here. Then simply go to assign floor loads. Go to assign pressure loads. Okay, now go to pressure load and assign pressure load. Here under assign pressure load, the direction of pressure force it is asking, it is phase, and it is global Z. Global Z, what is the pressure value? It is 76.4. It is here 76.4. Simply give it minus 76.4 and select the plates. Plate selected and click on apply. Here you can find that the pressure load is applied. Now to see the value, you need to go to here, the pressure load, and right click, and it will be display. So it is, you can see here you can see it is 76.4. it is written here, everywhere. If you take a single plate, then you can see the pressure load is applied, so minus 76.4. so there is nothing to be worried about. Now let me remove or on display these things, because it will not be better to keep these things. Now activate the whole structure and zoom out the structure. Now we have our original structure. So here our pressure load is applied, then we will apply it under live load as -2. Global jet, everything is same. Here only you have to put -2 as maintenance live load. The plates are selected and apply. It is -2. It is so meshed so that it is not you are not able to see it. Let me select it, the plates only, single plate I need to select and view, so that it will be easier for you to see. Oh, just have a look, it is -2. So now your dead load, live load application is over. Now we need to undisplay the things. We need to activate the whole structure, and here we go. Now what happens, your only thing left is your earthquake forces. For earthquake force, now again go to design data. Now here I have already calculated it for you. Total weight of tank including acid is 150 metric ton. Weight of pile cap we have taken as 850 mm for the calculation, but we have provided 1 meter thick pile cap, which we can modify also. It will be 850 mm. If we take 850 mm pile cap, it will be 72.3 metric ton. Then the seismic coefficient is, it is under zone factor 3, that is it is in zone 3, Z by 2. This is nothing but Z by 2, this is nothing but I by R, and this is nothing but SA, spectral acceleration normalized with G, SA by Z. So your R is 3. I have taken a little bit conservative. This is not that much of important tank, so it is of importance factor category type 2, it is 1.5. Then zone factor for zone 3 you already know, it is 0.16 by 2. To bring it down to DBE, from MC maximum considered earthquake to design basis earthquake, we divide it 2. So the coefficient comes, it is 10% of vertical weight. So horizontal seismic weight acting on the tank is how much? 15 metric ton, and horizontal seismic weight acting on the pile cap is 7.2 metric ton. Now let us remove. Now let us activate it. Now simply the seismic force, obviously will be acting at the center of tank and top of cap, because cap is a rigid structure, so it will be acting on the top of the cap actually, and for a tank it will be acting at the center. So it is 3.7 meter height tank, so the pressure will be acting at 1.85 meter. height, and for pile cap it will be acting at the top. The value will be how much? It will be for tank, it will be 15 metric ton, and for cap it will be 7.2 metric ton. Now let us come here. I will be directly applying it here. Let me opt the 3D grid model and go to your nodal load. This is the nodal load. Instead of nodal load we should go to element load. Select element load, beam element, select EQX, and it will be a concentrated force. How much? It will be in the direction of global X, and what will be the value? It will be relative, that means 0.5, 0.5, and the value will be how much? Value will be minus 15 metric ton, that means 150 kilonewton, right? So now you have to apply it here. Let me select it. Yes, we have to apply it here. Click on apply. This is, you can see from the negative X direction it is coming. You can also change it to positive X direction, there is no issue. If you do not want to put it in negative X direction, you can simply edit here on the tables. You can simply put edit it as simply 150 and it will be edited. Whether it is edited or not, you can find it here. Oh. Now it is applied. Now further, let me go to the top view. Again the center of pile cap is obviously here, so I need to select it. I need to go to that particular portion activation, and I need to activate the nodes to know it. From here our pile starts, that means the entire pile cap weight will be acting here, the concentrated force. Now go to the nodal loads. It is under earthquake X, R. In Fx direction you have to add 7.5 metric ton, that means 75 metric ton. Simply select the node and click on apply. So you have now your earthquake forces applied. It is to pile cap, and this one is to your tank structure. You can display it here, right? Here to see the tank, to see the cap load, you can simply click on display. In a very similar manner, we'll be applying the jet direction forces. I can simply put it here. Is 75. Then you need to select the node, then you need to apply. It is in Z direction. EQI, and you can select the node and simply click on apply. So your EQY direction load has been applied to your pile cap top. Simply similarly you have to go to the element tab, have to select EQI, the same process what you did for your EQX. It is, since it is a relative, you have to find point, you have to provide it 0.5, that is at half. It is instead of global Z, you have to provide it at global Y. Value will be how much? It was 15 metric ton or 150 kilonewton. Simply select this one and click on apply. You can see it is applied here, right? That 75 is constantly showing because I'm not on displayed this one. Now the forces are applied. Here you can see all the forces. First of all, your self weight is complete, then the pressure load in form of tank dead load is complete, fluid load, then it is live load. The live load is also complete, it is 2 kN per square meter. Then your nodal load, this load represents the seismic weight of pile cap acting at its top, then it is the seismic weight of tank, then it is again in Y direction. So these things are actually completed. Your loading part is complete. Now let me remove it. Now let me go to the whole structure and remove the node grid and activate the 3D, and everything is now fine. So from here we have to go to analysis option. Here you have to click the analysis tab and perform analysis. So Midas is performing analysis. Here you can see the solution time and things all etc. It has taken 2.79 or 2.8 seconds to complete the detailed solution. It is a very small structure, so very less time was consumed. Now you can see the structure is showing logged. That means analysis is performed and post processor is ready to take the any sort of design or combination of loads, right? Now let us go to results tab. In the results tab you can go to you can simply check the reactions here. Let me show you one demo. It is reaction forces. Simply you can check Fx, Fy, Fz for dead load, and you can check the value and legend both to be defined, and scale factor is this, and this one is apply. Now you have applied it. Now you can see the reactions. The reactions are written here. Let me provide you a grid view type structure here. The values you can find out here. values you can find out here. It is around 146, something like that, and also 164 and all those things, right? So maximum value what you are getting here is 146. Maximum value is here, it is maximum reaction. You are getting it as Fz is your 146, that is plus 2 means 146.47 kilonewton. Your unit is mentioned here, unit is your kilonewton, so it is 146.8, right? It has nothing to do with that. Now you can similarly also check the reactions after load combinations as well. Due to very less time, I am unable to complete all those things. I am just simply giving you another example is this, or you can simply click on Fz, so that you will be getting only Fz. The red color shows you the upward force that is acting under dead load. You will see that it is the maximum actually load that is acting there. So similarly you can find out here minimum and maximum reaction is there 186.4. This is your maximum reaction under dead load 186.45, and here it is minimum reaction under live load, it is 146.47. Similarly, now let us go to our load combinations. Here we have to go to concrete design, we have nothing to do with steel, and you have to auto generate. It will ask you the codes. Obviously it will be IS456 and no scale of factor, nothing, no consideration of orthogonal effect. What do you mean by orthogonal effect? It is something like what you say is in 1893, if the lateral load resisting elements are not oriented at 90 degree or orthogonal to each other in plan, then we have to take 30% extra of another orthogonal direction seismic force. That is, suppose we are taking 1.2 times earthquake X plus 1.2 times dead load plus 1.2 times live load. There we have to again add 1.2 into 0.3, that is 0.4 times EQY plus 0.4 times EQZ as well. That is the orthogonal effect. But here our tank is perfectly symmetrical. There is no meaning of taking any orthogonal effect. So only concrete portion will be taken care of. Now simply click OK, and you can see how smoothly the service envelope, here it is service envelope of earthquake XY, dead load, live load, everything is generated, right? Everything is generated here. So it is 1.5 times dead load earthquake, it is 0.9 times dead load earthquake, everything is generated here, right? So now let us close this. Now we will go to the design tab. Our analysis is complete, we will be going to the design tab. Under design tab, first let me have the IS456. First let me take the general parameters. So what is the definition of frame? It is showing definition of frame is whether the frame is braced, that is non-sway type, or sway type. Actually what I have told you from very beginning, piles being embedded inside the soil, it will be something like non-sway type frame. Generally it is a braced frame and braced by the soil, the surrounding soil. And effective length factor, you have to check it, auto calculate, you need not provide it, otherwise it will be taking as per the data provided by the user. So design type is a 3D design, simply click on OK. Then let me remove, actually simply let me activate the 3D, and this is our tank model. Now again here there is no need to provide any live load reduction. Then load contribution for non-linear we do not have. Member assignment is a different thing. On braced length it will be automatically be taken care of, because in under definition of frame you have calculated auto effective length, and so software will be automatically taking it. You need not provide here on braced length separately, you need not provide it here, it will automatically be taken care of. Then your equivalent moment, these things are only provided to your steel structure column design. So here we do not need to provide anything. Now let us come to IS 456. Also British code is there. Now go to RC design. Here it is, design code is here. IS 456, it is asking that moment redistribution factor for beam torsion design. Actually there is no torsion parameter involved here because there is no beam involved here. Whatever torsion is coming on the column or that pile, it will be automatically be taken care of by the software. It is only asking for the beam, so you need not take it. Then PM Corp calculation method, it is a US or ACI code method, that M by P constant, whether you need to keep M by P constant or P constant. We'll be explaining these things later in the detail design or in else our webinars. So I'll be providing it later in different webinars or something like that. It may be provided in Midas Gen detail course, because it will again a time taking procedure. So now here it is asking whether apply special provision for seismic design. We have already taken that we have taken response reduction as 3. That means we are not into the ductile design because it is very simple structure, so we need not apply this. Simply apply IS 456 2000. Now go to your partial safety factors. Partial safety factor for concrete you know, and steel is 1.15. update by code, it is updated. Okay, then you go to your modify concrete material. This is very vital, you have to select it here. Here you have selected M30, but here you need to select IS code, and grade of bar, main bar is AP 500, sub rebar is also AP 500, and accordingly you modify. So the main bar and your sub bar data is now available in the table, and now close it. Now go to here limiting maximum rebar ratio. All these things are actually preset. Once you select the code, means it is actually preset. Minimum section size for beams and column, it will be considering minimum beam size, as the minimum size of beam is 200 mm, though there is no 200, though beam are not available here. Next, all these things are actually already taken care of. So now we have to go to concrete code design. Here you have to go to the column design. Now let us come to concrete column design. Design is finished. So here let me expand and let me put all members. So let us come here to concrete code design. It's column design. Now it is designed, as you can see. Actually let me expand. So you can see that it is showing property wise. We can change it to, it is a member type. You can see pile 500, though the section name is written 500, but the diameter of pile is 450 mm. And okay, so here you can see the diameter is 450, the 500 is actually the name size, so let us keep it like this, but actual design is carried out using 450. And one more thing, you can just select anything like the summary sheet, you can get it from here, design summary sheet. The graphical presentation, you can get it here. Details, you can again select it from here. If you want to update your rebar, you may take this option. And so many things are there, and you can directly copy this table and paste in your output sheet while submitting the report to the client. Also, in a very short look, you can see the details rebars are presented here, 6 numbers of 20 tur rebar, and the spacing of 10 tur rings are also here. The grade of concrete is 30,000 kilonewton per square meter, that is M30 concrete. And similarly, it is actually the grade of steel is higher, it is 500 Fe 500. Let me remove all these things from screen and we'll see the options one by one. So now we can you may select only one for just for the sake of this webinar, and you can first of all click the summary. The detailed summary will be generated here. You can this is the intro on Midas, then you can see the summary sheet is here. The pile of 500D is showing there, and this is your steel Fe 500, and this is your concrete M30. And similarly, the rebars are presented here. First of all, area of steel required is presented in square meter, 0.0019 square meter. Then the number of rebars, 6 numbers of 20 dia rebars are presented here, and the section height or diameter is presented here. It is 0.45 meter. You can simply see the unit as meter here, so everything is presented in meter. If at all the unit is not mentioned, then it is by default meter. If it is mentioned, then it is that particular unit is taken care of. Like you can see here, it is 280, that is 280 mm only. Okay, so these are the presentation. Next we can go to the graphics. You can see the graphical curve here, and they are very nicely presented. If we go to a full screen, you can see it here. The same presentation is given here. It is the code. First of all, design code is there in the top, then the material data is there, pile diameter is there, section property name is there, length is there, everything is there actually. Then simply see the MN interaction curve, or you may say it is as PM interaction curve, and after that the end and middle part calculation is also there, the checks are also there, and the detail bar arrangement is also there. So it is a very nicely presented data. Further, you can also go to the details, the detail calculation. If you want to see, you can go to the detail calculation one by one. You only saw the summary first time. Here you can go to the detail calculation and detail checks, rebar pattern, everything. The detail checks are there. Computer design parameters. So everything, the calculations, eccentricity and the ratio, everything is there. Then followed by the design capacity of moments, then check for the M by MRD ratio, that is what you find it in code as M applied by M resistive to the power alpha. So then the shear check comes into the picture. After shear check, the steel calculation is there, and everything is there. So you can take directly print out of this. So we think our pile part is covered. Do it. Now let me close this one. Now let us come to important part, that is pile cap design, that is mesh slab design. Generally this feature is lacking in many available softwares, but Midas is very well designed to take effectively the pile cap design. Here it will be slab wall load combinations, everything. You see the deflection and crack check is taken care of by your serviceability load cases, and for strength it is up to 13. If you have forgotten, here it is the result, it is the load combinations and concrete design. Here you can see that up to 13 it is strength, and then it is coming the serviceability. So from 14 to 22 is the serviceability load case. So now let us come to design. So here you can see up to 13 it is kept under strength calculation, and for serviceability only 14 is taken. You can check all this. Also deflection it is generally check under dead load, live load, so it is as per your wish. You can take it or not. So simply click OK. And then mesh slab design criteria for rebar. Basic rebar for slab or mat, simply uncheck it, because it is the software defined data which we should not use. We should provide our own. For that, for slab design you can take the loads, the reinforcement from here. And for mat design, generally we provide in mat 16, 20, 12, 16, 20, 25, 32 is avoided. And then comes spacing. It is only 100, 200. We can also provide 125, 150, 175, and okay. Also the next comes to the concrete face to center of rebar. That is it is asking me the cover. Since it is in a hazardous environment, the cover is 75 mm. Assuming that we are providing 20 mm dia steel, though, so the middle of the steel will be 10 mm. Since the rebar is 20 mm, the middle will be 10 mm. So 75 cover plus 10 mm your center of the steel. That means total will be 85 mm. So you can provide 0.085 meter. Here very same under direction 2. Right, here we do not have any wall, so there is no issue. Okay, now click on OK. Design results will be deleted. Continue. That is asking, it is asking you that the design results of piles will be deleted, because only at a time it can design either plate or your line element. So we are okay with it, because I have shown you the pile design results. Now let me go to the slab flexural design. Here we have taken, first of all, it is all combinations. Instead of any single combination, we have taken all combinations. One important thing is here, yes, one important thing, let me activate the nodes. Actually what it is asking, the flexural design will be performed for each element or average of element. That means the average of these 5 elements will be the node. So it is asking whether it is average or single element wise. You see, you have to understand carefully, either you have to take element wise or you have to take suppose here I am taking these 4 elements. Instead of taking 4 elements, the corner of these 4 elements will be concentrated here in the node, that is 735. It is asking whether it is upper nodal. Generally in FEM we have to take the average nodal, because it will be smoothening our stress flow. Instead of local failure, a global failure is observed. So average nodal is more appropriate than element wise. So under flexural design, first of all it will be average nodal. Then either you may take 1 meter width strip, or you may directly take element per mm. It doesn't matter. Then whether you want to take the top reinforcement or bottom reinforcement, it is up to you. Then your direction 1 or direction 2. Suppose your direction 1 is x axis and direction 2 is y axis. So it is up to you what steel you want to know. Since it is a pile cap, so the steels will obviously be same in direction 1 and in 1 and 2. Then comes your type of display. You only want contour, legend, or contour legend values, or none of these, or any one of these. It is up to you. You can check or uncheck. It is as per your wish. Then comes your one way flexural. We lack one way shear. We lack one way slab here, so we need not design it as one way flexural. Then it is asking whether you required your AST requirement or rebar. Wood armor moment, you see, wood armor moment is something that is applicable to slab, and also the design is taken from the wood armor moment only. However, it is asking you whether you want to know the value of wood armor moment. If you want, you must select it, otherwise you must simply select rebar. And now you can have your apply. You can see the software is doing the design, and design is complete. You can see 16 torr 150 center to center is presented here, and you can see here 16 torr 100 and 16 torr 150. 16 torr 100 is only in this region because it is a highly concentrated region at the center. All other spaces it is 16 torr 150, right? You may also see as per your wish only contour. It is up to you. It will be better and nicer to recognize. Yeah. Now let us come to update rebar. Now apply your slab shear checking. Now rebars are updated, and your slab flexural checking. Slab flexural checking is also complete. Now go to slab shear checking. Here we first need to check the punching shear. Here, in case of your punching shear check, parameters are overlapping as per the software warning. Yes, either you see you have to either increase the thickness here. It is not a very issue. You can clearly see if I go to the whole structure. You can see the, let me off this. You can see the punching shear area in the circle. So but what are the results? If you go here, you can see the punching shear is okay. It is giving you only a warning that the punching shear area is overlapping, otherwise punching shear is okay. Here you can see it is okay, right? So no extra reinforcement is required, right? it is also here. Okay, you need to draw some of the lines from here to here, the cut line. First you select the point 1 here and the point 2 here. You can select the point 1 here to point 2 here and click on add. Similarly, you can select here to here, click on add. You can also go to corners, add, also you can add. So in these areas actually keep it reversed so that graphs will be clearly visible, and in these areas actually how nicely it is done. How nicely it is done. You can see it, the shear force diagram. Now you can go to design results, and you can also find here it is shear force is also okay. One way shear is okay, and two way shear, that is punching shear, is also okay, right? So this almost completes the model in Midas Gen design and analysis. Earlier we had some pile arrangement like this, right? So per one pile we had 178 kilonewton. This was our case study what we did. That was for how much? Dead load plus live load. That too, these are unfactored. Unfactored. That means no factorization word was added to this. So one pile, if this is the pile, if we got a section AA, it will look like this. Section AA, there will be vertical bars. The numbers you should not count. We will be proceeding to design and you will see that. Okay, so the our 450 dia pile, here to here it comes 40. So 140 dia pile was capable of taking 178 kilonewton load. Now let us come to our software. Here after analysis we'll be going to the results. Now here click on results, click on reaction due to forces and moments. Here select combination 14. Prior to that, let me come to load combinations. Under load combinations, we have selected concrete design because ultimately we will be designing the pile and pile cap using our RCC code IS 456. So here our service case is starting from here. The service of the load case, our load factor is 1 and 1 per day load, live load. For earthquake, I have not done the manual analysis because manual analysis in today's scenario, in the presence of software, I do not think it is more time consuming. So I do not think personally that if our software is able to give, why should we delay the project by going to manual analysis? And also manual analysis assumes several load data and also several boundary conditions are being assumed. It is better to go for the software. So our load combination 14 was representing the total gravity load, that is unfactored, one time dead and one time live. Let me click on values and legend so that it will be presenting the values as well as a graphical or a legendary format of the stresses or the forces. I have selected FZ here instead of FXYZ. I have selected FZ so that the vertical forces can be compared. Similarly, the horizontal forces will be comparable. I need not waste time on that because our basic motto here is to provide you the details of software analysis. So now let me click apply. Here you can see, let me come to the board writer. Prior to that, let me keep this model little bit rotated so that you will be able to find the values actually. Yeah, this will give you a better view. Yeah, here we come. Now you can see that here you can see the FZ. This is the legendary presentation. Unit is kilonewton. Okay, so here what you can see that the FZ value is 1.8112 E002. That means it will be ultimately 181.12 kilonewton. Alright, and this value is here. So you can see that our hand calculation was 178.8 and it is coming 181, so very close. So software results are almost similar, and you can also see that there are several other things are there which we did not calculate in hand. We just went for the maximum loaded pile in hand and it gave us the result. Now let me give you another thing. That the maximum result is obtained not at the outer side, because we assumed our pile cap as infinitely rigid in case of our conventional analysis. However, in practice our pile cap is not infinitely rigid, it had some rigidity, so which is being taken care of by the software effectively. So the instead the result, if you see, you can see here our maximum result is coming here, but in manual calculation we calculate the maximum result to be coming at this point. So why this has happened? Because actually the mass or the entire load is concentrated in this area, because this is our tank area. So actually entire mass is concentrated there, but we assumed that the entire pile cap is a rigid structure, so it distributes the loads uniformly on the piles. But this is a assumption only in the absence of software. When it was earlier in let us say late 90s or prior to that, when scientists wanted to design pile caps, so they had to go for some assumptions which will ultimately be reflected at field. Whether we are taking 181 is here or 181 there, they are concerned about the pile reaction, so that they can go for punching shear and your other shears checks. But actually, since our loaded area is here, so it is very obvious that maximum load should occur within the loaded area, right? But since we have assumed that the pile cap is infinitely rigid and it will be taking or it will be distributing the loads uniformly on the pile when applied axially, so as per our assumption we got the result maximum portion here in case of our hand calculation, but actual case is just below the tank. Very similar thing also can be simulated, but since it is FEM result, and if you understand FEM properly, FEM is a numerical software, and there are two regions here. For deviation there are two regions. One is the numerical software, it is numerical. Unlike hand calculation, it will not give you any closed form solution. Closed form or exact is not given by FEM, right? It is a numerical application of software. The next thing is what? It is more exact, or better to say more practical. And less assumption, right? It is giving you more practical, less assumptive results. That is why the values differ, but our main concern is ultimately the values on the pile. One pile should be carrying a load of 178 as per manual analysis, and as per software it is 181. That is nearly close. Your 178.8 is very close to your 181.1. Ultimately we need to design for that. Similarly, we can go for the shear checks and punching shear checks, and we can find out the results, right? So I am not proceeding to the comparison more, because if our audience wants, we'll be going for another webinar describing in details between the comparison study. But for this webinar we are very limited to this pile, because already lots of time are being taken and still design is yet to be done, and after that I will be showing you some of the economical design aspects. So there are lots more to come, so I am limiting it to the piles only. If required, we will be going for higher analysis. But keep in mind that in FEM, closed form solution or exact solution is not obtained, so always will be finding a solution in certain ranges, not exactly is equal to that, right? So let me come to the design part. So now let us come to the economical aspect of design. If we, let me come to the 2D, come here and activate the nodes, right? So here what we can get is that actually the distance between the pile, actually the length of the pile is 10 meters. So what we can do, we can go for okay, so we can go for the other lengths. Like if I go to front view and suppose I divide the pile to several parts. Or you may try that we can better, we can go for dividing it. Sorry, let me go to the point spring. Here we can provide the value. Let me give STX and STZ as 5000 kilonewton per meter, and let me select the points. Bottom one is your fixed one, so we need not touch the bottom, and we can simply click on apply. That means, and we can go to whole structure here, right? Here we can simply, we can activate it, right? So these are the supports, point spring. Here it is highlighted, you can see it is highlighted here. This area, okay. So now point spring is also available. So now we can go to further analysis. This will only restrain the pile against translation, but vertical load will be taken care of by pile itself. Now it is, analysis is complete. Now we can go to here our design. Here we can go to our RC design, and we can go to concrete design code, column design. Here you can see the details, the pile 450 dia, what is the area of steel required. We can also see now, you can see the graphics. Select it, then go for graphical result. Here you can see 6 numbers of 20 ton steel is provided. Definitely little bit reduction in area has been achieved. Earlier it was 8 20 ton, as I can remember. Now it is 620 ton. This way you can also reduce the requirements. This is just the possibility I explored, but in this project what we did not take this into account because it was industrial project, and generally what happens during construction, lots of faults are there, and since it is a acid tank, in due course of time, whether we admit or not, acid will be percolating, right? So it will be also hampering the life period of the concrete. So generally for industrial structure we go for little bit heavier design with a little higher factor of safety or little higher margin in design. So I just explored the possibility how to economize. So now let us come to the conclusion part of this webinar. It is already too late. I mean, it is not late. We went very fast. But thing is that our audience must be bored by this time. If you do not understand properly, you must be feeling bored. Anyway, so thank you for watching all with patience fully this webinar. Anyway, so I would like to thank all the audience for that, and with in future we'll be coming with such webinars as well, and we would like to highly appreciate whoever is going comments and for any further improvement or any shortcomings that we have left or something like that. And we would also try to involve more academicians and more practicing engineers of this industry as well as construction industry from all sort of industries of engineering, and we'll be conducting the webinars to enhance the knowledge and the skill set, and also to share the practical experiences including the design drawings as well as in highway sector as well. So also in geotechnical aspect, as I have already told, from process engineering to manufacturing engineering, everywhere we will try our level best. For now it is limited to structural engineering part, but very soon it will be expanded to several parts. Also in structural engineering, we would like to inform you that our other speakers will be coming soon, and we expect the same cooperation from yours, and we expect that this knowledge sharing platform will be expanded further and further, so that India, actually if you go to industries, you will find that India imports every sort of technology from outside. Even I can say it is more than 90%. And particularly speaking about regions, only a few regions have the industrial expertise. That too, that they are also the market of big players. That means the foreign consultancies and developers are there who are having their office in India, and they are running the whole system. So the aim of this group, that is the AANKHE group, is to develop not only engineering here but also to exchange our knowledge, so that in India we can indigenously develop the technology and we should not rely on the others, right? India should also export its technology to outside, like it was doing in ancient time. So anyway, already lots of times has gone. So for now I would like to say thank you, and we'll be meeting very soon, and we'll be notifying you all. Thank you.